All right, we're recording. Good. All right, so we left off over here, verifying two functions or inverses. Okay, so remember, what does an inverse do to its original function? What's the purpose of an inverse? The word I'm looking for rhymes with fun does. Undoes. Thank you. Thank you. Undoes. Yeah. It undoes the work of the other function, right? So if I'm standing literally, you see this X right here? Y'all in the front row can see the X where the floor tiles intersect. I'm literally standing at X marks the spot. If I have one function that takes me 2 steps to y'all's left, then the inverse function would take me 2 steps back to my right. And look, I'm standing right on the X again. Now I went left and then right. What if I went right and then left? 2 steps to the right and then 2 steps back to the left. Am I still where I started? Yes. Okay. So composition of two functions in general is not commutative. It matters the order in which you compose two things. If you're going to take some $10 off versus a $10 rebate and you can do both, it matters. You're going to get more money off if you take the rebate first. But when is composition of functions commutative? It's commutative when the two functions are inverses. So here's what we could say. If f of f inverse of x equals x, and f inverse of f of x equals x, then the two functions are, in fact, well, yeah, they're in fact inverses because look, we're starting with x. We're doing the inverse function first, which takes me 2 steps to the right. And then we apply the next function, which undoes it, 2 steps back to the left. We're right back where we started with x. See that? Start with x, 2 steps to the right first, and then 2 steps to the left first. We're back at x. So start with x, end with x. I'll show you what I mean. Use composition to verify that those two are inverses of each other. This one is f of f inverse. We need to show that it's equal to x. So here's what I would do. Start from the outside. What does our function f say? F says, well, we don't know which one is f. Let's call this one f, and we'll call this one f inverse for now. Okay? Is it actually a function? It is. It's linear, but let's make sure they're inverses. All right, so f says that I do 1/2 times the input plus 5. That's the function f. And now what do I plug inside there? I plug in f inverse. What is f inverse? It's 2x minus 10. 2x minus 10. So into the function f, instead of placing a number, like 1/2 times 1 plus 5, I put a whole other function, f of blob, right? Here's what function f says. Function f says 1/2 blob plus 5. 1/2 of something plus 5, right? 1/2 of something plus 5. All we're doing right here is we're plugging f inverse in for the something. 1/2 of something plus 5. Got it? That's called composition. We're physically plugging one function into another. Now all we got to do is what? Multiply it out. I call it hit sledgehammer. Hit it with the little sledgehammer. Dink. And you get x minus 5 plus 5. And lo and behold, the 5's cancel, and we get x. Cancel. Yeah. Nice. That's what we were expecting. Let's try it the other way. Now we do it the other way. Now we start with f inverse on the outside. So now it's 2 something minus 10, right? F inverse is 2 times something minus 10. But what are we going to plug in? Yeah, we're going to plug in f. 1/2 of something minus 10. And that something is 1/2 x plus 5. And now once again, all we have to do is distribute, right? 2 times 1/2 is 1, so we get x plus 5 times 2 is 10 minus 10. And lo and behold, once again, the 10's cancel. And we're left with x. Again, once again, we see that the math reveals to us that it's x in both cases. And therefore, since f of f inverse and f inverse of f are the same and they're x, what do we know about those two functions? They're inverses. So now you would say, since f of f inverse of x equals f inverse of f of x, you're basically just writing those two things up here. since this and this equal each other, and they both equal x, comma, f and f inverse are, comma, in fact, right? We'll add that, in fact, inverses. Oh, hi. We were doing math. I didn't even see you there. Thank you. Okay, yes, she's here today. So any questions? Pretty good? See, now this is where normally I would give y'all two to try on your own in the notes, but it says y'all do that in the worksheet, in the homework. Yeah. And see, I only work one of them. Is everyone okay with what I did about plugging in? Okay. If you're not, let me know. Let me know. You just found the inverse and compared it? That's another way to do it. That's another way to do it. She just did what we did in the warm-up. She switched x and y and found f inverse and compared it to the other one, and it was. And certainly that works. On the test, though, if I ask you to do the composition, I would kind of expect to see it. It's a good algebraic skill to be able to plug one thing inside of another for x. But that's good. Well done, Sloan. You didn't say not to, right? All right, any other comments or questions before we move on? Moving on. Would anyone like to stand and read this? In a model for a real-world situation, the variables have specific real-world meanings. Duh. For example, the distance miles traveled in time at a constant speed of 60 is 60t. Yeah, that's the distance equals rate times time equation. I call that the dirt equation. Distance equals rate times time. Distance equals rate times time. And that's when the rate is a constant rate. Writing it in function notation is d of t equals 60t. Emphasizes that this equation describes distance as a function of time. Yeah. So the dependent variable is the y variable. That's the independent variable would be the input, the x. You can find the inverse function by solving for the independent variable. Writing in terms of dependent variable, this gives the equation. Right. Okay, that describes time as a function of distance. Because the meanings of the variables can't be interchanged, you do not switch them as you would switch x and y when working with purely mathematical functions. You may also have to restrict the domain and range. Yeah, so it's really hard when we think of distance as time as a function of distance, right? This just means you don't walk around with we walk around with a watch on our hand that tells us how much time has passed. We don't walk around with a measuring stick measuring how much distance we've traveled and say, oh, it must be time to leave. No. So that's what they're saying. When you interchange x and y, you can't do that. You have to keep the variables with them. So we would measure, well, I'll show you what I mean on this one. For the given function, find its inverse and graph it. Determine the domain of the inverse. Interpret the meaning of the inverse. Okay. A municipal swimming pool containing 600,000 gallons of water is drained. Uh-oh. I bet someone peed in it, huh? Nah, they don't drain 600,000 gallons when someone pees in it.
How much is that?
That's a lot.
Like 600,000 gallons.
600,000 gallons. It's a little over 500,000 gallons of water. It's a lot. And if someone pees in there, they just shock it. And then more people pee in there and they just shock it again. No, they don't even. At some point, they don't even. Right. It just gets absorbed.
My brother
It becomes water.
works for a pool company.
Oh, yeah?
Or he does.
Yeah, yeah, yeah. Don't pee in their pool. They don't swim in your toilet, right? So, a municipal swimming pool, okay. The amount of water W in thousands of gallons that is drained, remaining in the pool at time t hours after the draining begins is that. Okay, so notice if we were to graph this, this has an independent variable of t, so that would be the x-axis. And then this would have your dependent variable, which would be w on the y-axis. And that graphs as a line, right? It's up here at 600. And then minus 20t, it's going to be going down, something like that. And when is the pool empty? Right here. Yeah, so this line would actually extend out this way. But the part of the graph that we're interested in the real world, is this right here. Okay? And the slope represents the rate of change. This would be the water in thousands of gallons, and this is time in hours. So the slope means this, the negative 20, just,
The graph on the side has it flipped.
yeah, because, we're not doing, this is not the answer yet. Yeah, this is not the answer yet. I'm getting to there. Yeah, it does have it flipped. I'm trying to get you to interpret this, but thank you, Cannon. Negative 20 is going to be negative 20 gallons per hour, okay? The slope of the line is your rate of change of y with respect to x. That's getting into like calculus stuff. So this water is draining at a constant rate. It's draining at a constant rate of 100,000. So 2 million gallons per hour. Is that what that is? Or what is it measured in? In thousands of gallons. Okay, so 20,000 gallons per hour. Every hour this thing drains another 100,000 gallons. But what it wanted us to do is it wanted us to flip it around. So when we solve the other way, we can't just flip, we have to solve. So let's do that. Let's take W equals 600 minus 20t, and now we're going to solve for t. So we get 2t equals 600 minus W. How did I do that? I just brought the negative 2t across here on the left, made it positive, and I just brought the W across on the right and made it negative. It's like a double shell move. It's real easy to move things across the equation.
20, 2T,
2t?
20. Yeah, how do you get it? It's 20.
It's 20. Oh, how did I get 2? I just wrote it wrong. Yeah. Yeah, no, thank you. It's 20t. 20t. It's not 2t. 2d. 2d. You said it too. 2d. Now we'll divide through by 20. So I get, I'm going to put it in slope-intercept form. So multiplying through by 1 over 20 or dividing by 20, I get negative 1/20th W plus, and then 20 divided by it gives me 30. So all I'm doing is I'm solving for the other variable. We don't typically do this. Again, this is like measuring how many gallons have leaked out and then measuring, going to check the clock, right? But if I graph that, that's going to look like this. There's your y-intercept, and it's down 1 and right 20. So it's going to look something like this. We could find another y-intercept, 0.30. Yeah, it's going to look something like, it's going to be that one reflected across the line, y equals x. So it looks something like this. Yeah, as more water drains, there's less time. Oh, time draining. This should be what? Positive slope. Did I get the slope right? Minus 20. It's K. Okay, got it. 20t, 600 minus W. Oh, yeah. Negative 120 plus 30. That was right. Mhm.
Is it down 1 hour?
It's down 1 hour and right 20, or you could say it's down a 20.
Then it's a lot deeper than that. Yeah.
It's very shallow, actually.
Look at the, yeah.
It's very shallow like this. Yeah.
Going down.
If you take the line that we drew right here, this first one, and I didn't draw it to scale, right? But if you reflect it across the line y equals x, you get the same line. This one should be a lot steeper, and this one is less steep. I just didn't draw it to scale. But you go down 1 and run 20. But you got to look at the scale too.
You have to go all the way down to 20.
No.
No, 20 on the. Oh. I was thinking 3 minus 30.
Oh, yeah. 600. Is that okay? Yeah. So we solve the equation that they give us for the other one. I don't even like this question. I don't like the way they're asking it. There's really not a reason why we would want to do this, but except for to get you to solve for the other variable. Okay. And they're not really drawn to scale, so you're not going to actually see that one is a reflection of one across the line y equals x. Okay, so as long as you can just solve for the other variable, that would be good. And just know that it has a negative slope and a positive y-intercept. Okay, it's the opposite. Okay, sorry for that confusion. That's not my favorite question on here at all. Let's look at the practice test, or the review, as it's called, right? So I'll get it with you. Canvas. Enjoying teacher? It's asking me. Not now. Shh. There's a time for everything. Now's not the time. What do inverses do? They undo the work of a function, right? That's what they do. Chapter 2 review. The answer key is there, so you can work it tonight if you want. It looks very similar to your quiz.
I can't connect to Wi-Fi.
I don't, but it probably looks very similar to the review. Okay, how about we do this? I want to make sure I'll get y'all's quizzes back today. So let me just take the rest of the period to put those grades in, and y'all can work on the review, or you can work on the homework. Okay, and I'll take a look at the test real quick, and kind of give you a heads up.